Hi everyone, my name is Don Knight. I'm a retired aerospace engineer with a hobby of computer simulation. I'd like to share something with you that I learned that was valuable in my career. It's a mathematical tool called least squares. Um, I have my roots are in San Diego. I grew up in La Mesa, won awards at the Greater San Diego Science Fair, went to Grossmont High School, went to San Diego State for a degree in physics. After that, I went to UCLA for a master's degree in engineering. In my early career, I worked in the radio group at Jet Propulsion Lab, JPL, in Pasadena. I wrote a computer simulation of the Voyager spacecraft radio and used the simulation to predict receiver and nonlinear effects and set design parameters. After that, I went to Magnavox Research Labs in Torrance, California, where I helped design the very first GPS receiver that's ever built. It was the Magnavox X-Set in 1975. I'm currently living near Big Bear. When I was a young engineer, we were using slide rules. It's true that we went to the moon on slide rules, but least squares was a difficult topic. It was never taught in high school that I know of. Um, we used least squares to fit lines and polynomials, and that was pretty easy. We knew about the Gauss-Newton algorithm, but a more advanced project like orbit determination or certainly solving for an unknown planet would be a graduate level or a PhD level project. A lot's changed since then. Any engineer who wants can have on his or her desk a computer that's 1,000 times faster than a mainframe was just 50 years ago. That additional computing power has added a wrinkle to least squares. It's made it much easier to use, much more fun, applicable to a wider range of projects. And I think it's brought it within reach of high school students. Um, this is a video. Primarily this is a mathematical topic, and I want to target an audience of high school 10th, 11th, and 12th graders. So for I looked at high school curricula to find out if it's changed since I was a student. I'm impressed that 12th graders are now getting some introductory calculus. So for those, this video will fit right in. For 10th and 11th graders, part of this might be challenging. If it is, just pick up a few ideas. There's no quiz. I'm going to use I'm going to stick to high school mathematics and use two cookbook software routines. And those cookbook routines are numerical integration of ordinary differential equations, commonly known as Runge-Kutta, and Powell minimization of functions. The Runge-Kutta, or what I'm actually using is a Gragg-Boullier-Stoer, will take a differential equation that looks like this one, x dot equals f of x of t, x dot equals f of t and x. It'll change that into an ordinary equation like this one. High school students can read a differential equation, but solving it is more difficult. You can certainly deal with an equation that looks like this because this is an ordinary equation. For that matter, there are differential equations that nobody can solve because, for example, just a three-body orbit. No one has ever solved a three-body orbit in the general case. The two-body orbits were done by Kepler and Copernicus and all of those. The other function is minimization, Powell minimization. What that does is it's a function that it takes a function of a set of coefficients and it finds the coefficients that make that function as small as possible. You'll if you were to go into those, read the numerical recipe, read the book on that, or delve into how those algorithms work, you'd be into calculus. You'd need college level math to understand those. But if what you want to do is use the routines, then just simply having a vague idea for how they work is enough to use those routines to get answers. I could start talking about least squares by rattling off a list of why engineers like least squares, but it would be jargon, engineer speak, or shop talk. So rather than give you a fire hose of jargon, what I'm going to do is back up and slow down, and I'm going to start by defining all the terms I'll be using so that 10th and 11th graders are all on board. So parts of what come up next are too elementary. Just be patient. It'll pick up. First of all, where does the name least squares come from? Well, least is the smallest of something, like this least is a family member here, least in age or weight. And a square is a number multiplied by itself. So least squares is going to be the smallest of a sum of numbers multiplied by themselves. I'll use vector notation a lot. A vector is just a bundle of parameters. Mostly it's just easier to write out a list of parameters. Like it's easier to use a vector to express a list rather than to write out the whole list. But it's the same either way, whether I write it out or just put a vector in the notation. A vector can also represent a physical quantity that has both magnitude and direction, like position, velocity, gravity have both a magnitude and a direction. Other authors will use put an arrow over something like this to show that there's a vector, or they'll boldface it. I don't use those, not here anyway. I'll use an underscore to represent a vector. So anywhere you see an underscore, that means that's a vector. Functions can have more than one variables as arguments. They can also have vectors as arguments. A simple x squared plus y squared is a function with two arguments. You can have a function that has a single argument, this x here, if the a, b, and c are fixed, or if a, b, and c can vary and x can vary too, then you really have a function with four variables in it, four arguments. And rather than write out f of x, comma a, comma b, comma c, it's easier sometimes to just write out f of x with an a underscore, where a represents that list of coefficients. In particular, when we get into least squares modeling, the model functions will have the form of a function that has a single independent variable as its argument and a vector as its argument. So that should look familiar when we get to it. The sigma just means to add things up. This reads the sum for I equals 1 to n of r sub I squared. All that means is, all it's just fancy notation means r1 squared plus r2 squared dot 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 rn squared. So that's just a shorthand. For those who haven't had trigonometry yet, I'll be using sine, cosine, and tangent. Those are the ratios of the sides of a right triangle. So the sine is this y over the hypotenuse, cosine is the x over the hypotenuse. The tangent of this angle theta is just y over x. A lot of times we know what y and x are, and we're trying to find what theta is, so that this theta is going to be the inverse tangent, the arctangent of y divided by x. A dot over quantity means its time derivative, or its rate of change. The rate of change of position is velocity. Rate of change of velocity is acceleration. The idea from introductory calculus is that if you have a change in position, a delta position, divided by a change in time, so delta time, then what you've got is the average velocity over the interval. And the idea from calculus is that as this time interval is in the limit, as that time interval goes to 0, that the average velocity converges to an instantaneous velocity. An experimental data set is a collection of pairs. Each pair's got an independent variable, shown here as x, and a dependent variable, shown here as d, for data. Usually x is something that's controlled, like time of a measurement, and d is the value of the measurement. Those are going to be indexed for I equals 1 to n, where n is the number of observations of the number of measurements. Okay, so here's an example of a data set. This engineer on the right has collected these numbers. This data set is indexed from 1 through 40. It has an independent variable x, runs 2.53 down through 22, and it has a set of data that's got a measurement associated at each of those times, or whatever x represents. So when you've got the first thing we want to do when you've got a set of data is to plot it, because sometimes rather than study the numbers, a plot will, something will jump out visually that isn't immediately obvious from the numbers. So this is a plot. of that data set we just looked at. And it looks like there's a trend line here. It looks like there's a strong trend. There's some sort of relationship between the independent variable x and the dependent variable d. So it looks like there's a very strong trend. It could be the whole purpose of the project might have been to demonstrate this trend or demonstrate some sort of a relationship within the data. So once you've got a set of data like this, and you've got a line, how do you set the line? How would you get the best line? You could, well, I'm getting ahead of myself. If you have a set of data and it's got a strong trend like this one does, you would postulate a math model that explains that data. If you're the engineer on a project, you've got some ideas of what's the relationships between your data, and again, the whole point of your project may have been to show that relationship or to measure it. Here, since we have a trend line, the math model would be that this is a trend line. The data is given by a trend line plus some error. And the error is just some small random numbers. In general, instead of this math model is a line. In general, you'd have a math model, or more properly, a model function that has an independent variable x and a list of unknowns or list of coefficients in this vector a, where a is just some list, a, b, c, d, e, whatever's in that. So a good model will make this equation true. You have your data is your math model plus some very small random errors. If these errors are not random, or they're large, or they're systematic, then that would mean that something's wrong with the model. Okay, so how do we solve for the trend line? You could lay a ruler across it. You could take a string and hold a string over it and slide the string around until it looks good. I've heard it suggested that you draw a box around the data points and then divide the box in half. You could take a point near each end and solve for the line that connects those 2 points. All those are good enough. I mean, you call those eyeball solutions. They're good enough for some purposes, especially good to get initial estimates of things. But if you want the best solution, first of all, you have to define, what do you mean by best? Best with respect to what? You can't tell a computer, go solve for the best line, because it will come back with something like specify parameters, please. So you have to define what it is, what best is with respect to. You need a metric for measuring best. An example of a metric is miles per gallon. So you can say that one car is more economical than another because it gets better miles per gallon. Your metric is miles per gallon. We need a metric here for least squares. So to get our metric, first let's zoom in on a single point. We've got a trend line. I'm going to take a single point, like maybe right there. It's offset from that trend line. Okay, so there's your point. It's offset from the trend line. Trend line is y, and y equals ax plus b. The difference between this point and the trend line is the residual at that point. In equations, the residual is d, the value of the data, minus the trend line for that point right there. That gets you your residual. If you change the values of a and b, then what happens is the residual change. But the residual changes not because the data changes, but because the line moved. And we're going to be moving the lines around, looking for the best line. In least squares, the metric for quality of fit is the sum of the residuals squared. So here we have the residual from the last slide. You take, and that's index for index equals 1 to n. You square those and add them up, and that sum is this function s. So the sum of the residuals squared, it's the sum for I equals 1 to n, residuals squared, or just written out, looks like that. This sum is a metric that says how good a and b are. So if you change a and b, the sum changes. Here we have that original blue line. The sum of the residual squared for that blue line is about 2. If you move off to a line that's not quite as close, clearly this line doesn't fit as well as this one does. The sum of the residual squares, it bumps up to 32. And if you take a line that's way off, like this orange one, the sum ways goes up to 294. So this is something you can tell a computer. Computer, get me the line that has the smallest sum of residuals squared. And that would be the least squares. That would be the least squared solution. It's a good idea to know what S looks like. Here we have on 2 horizontal axes we have the A, the slope of the line, and B, the y-axis intercept. And on the vertical axis we have the value of their sum of residuals squared. And ideally the S looks like a bowl or a hammock. And if we're trying to find the values of A and B that makes S as small as possible, that's equivalent to sliding down this hill till we get to the bottom of the hammock. So formally, we want the A hat and the B hat that make A hat and B hat that make S of A and B as small as possible. Formally, that would mean that S of A and B is greater than S of A hat and B hat for all A and B. That would be a formal definition of the minimum. And that A hat and B hat that makes S the smallest is the answer. It's the least squares solution. So at this point, the classic approach to least squares is just getting started, because the next thing they're going to do is they're going to use calculus of variations to solve for the minimum. And at that point, the whole thing gets very mathematical and gets very advanced. Usually you need college level work to even read past the first page. We're going to avoid that. We're going to take a different approach. We're going to use direct search. I'll show the classic approach for the case that we're working on. For the example we're working on, it's a linear regression, and the classic calculus of variations has a particularly satisfying solution in that case. We're going to use the direct search. I use PAL minimization for that search. So let's go over. I'll show you what the calculus. I'll show you these two approaches. The idea of calculus of variations. If this isn't familiar, then don't worry. You'll get it later in high school. The idea of the calculus of variations is that if you have a function, if you have a curve, its minimum occurs at the point where its slope is 0. So what you do is you get an expression for its slope, you set it to 0, and then you see what you can derive. For the linear regression case, the one where we're trying to fit, we're trying to fit a trend line to our data, that trend line is as AX plus B, and we subtract our data. That gives us our residuals. Square those and add them up to get the objective function S that we want to minimize over A and B. To do that with calculus of variations, that's the same problem in either calculus of variation or direct search. We're doing the same thing in both of these. For the calculus approach, you would take the partial derivatives of S with respect to A and with respect to B, set those to 0, and you work on down to an equation that looks like this. It's in a matrix form. And this is I've seen this in high school curricula. You'll run across that. It's not a bad solution. If what you want to do is fit a line to data, and you want to put together a software that's going to do that, this is a good way to code it up, and you'll use that solution. We're going to use that solution here in just a minute. The other approach, the direct search approach, uses software. It's a type of software that is literally called steepest descent. What it means is the software figures out the the direction of downhill that's the steepest, and it travels in that direction. To draw an analogy, if you were a skier and you're on a ski slope and you wanted to get to the lowest point in the local terrain, what would you do? You would figure out which way is downhill. You ski in that direction until it starts going up again. Then you'd calculate a new direction. Find a new downhill direction, and you'd ski in that direction until it runs out of room. And you'd follow the valleys on down to the lowest point, which it might be that point right down there would be the lowest point. Anyway, that's how in a nutshell, that's how steepest descent algorithms work. Again, if you would get inside the algorithms or get inside of numerical recipes and read about it, you'd need calculus to understand that. But if what you want to do is use the software, all you need is a vague understanding of how it works. So I'm going to run the software. I'm going to run it two different ways. We use a classic solution for that line, and we use a direct search. And the result of this software that's about to run is going to be to produce estimates for the line, for the slope, and B, the y-axis intercept. Okay, so we're going to run the software. It's running. Okay, software ran, and it pops out some numbers. The classic solution for the slope of that trend line was 0.297 ... The direct search algorithm gave 0.297 ... You can see they're the same, out to 12 digits. Same for the y-axis intercept, the b hat. Classic approach gave us 2.676 ... The the direct search PAL minimization gave us 2.67, exactly the same, out to 12 digits. The point is, those approaches are equivalent. If what you want to do is minimize the function, you can use calculus, or you can use a direct search, and you get exactly the same answers. So we're going to use that as a justification for using direct search. In this particular example, we know what the truth value is for A and B, because I know what the truth is because I used a computer simulation to generate the data. I simulated a trend line and put some small random errors on top of it. So the least squares is trying to average through those small random errors, and it does a pretty good job. The truth value is 0.3 for the slope, and the least squares comes with 2.97, which is very close to the 3. And the only difference, if I had simulated the data as being exactly on the line where those random errors were all 0, then this number here would have, instead of coming out 2.97, it would have come out exactly 0.30. And the same thing here. The truth value for that y-intercept was 2.7, and least squares is giving 2.67. Those are close. So once you've got your data, once you've got your estimates, you put those back into your reports, and you write up your assignment or your project, whatever it is, and you're going to have your data in there. You're going to have the plot of the data, the trend line on there. You're going to have your model function. In this case, it's a line. It's ax plus b and the coefficients, and you can wrap it up at that point. If once your math model matches your data, it looks like you're doing some really good work. So I want to pull together in equations, what we've covered so far into a single slide. It's a least squares problem statement. And if you can read this, then that means you've got the crux of what you're following along well. You've got the crux of what we're talking about here. So you will have a data set, which is a collection of pairs, for index for I equals 1 to the number of measurements, or the number of data items. For each item, you'll have a residual, which is the difference between a model function. The model function takes as arguments an independent variable x and a list of coefficients. This A is a list of coefficients, A, B, C, D, E, whatever's in there. The model function will take these as arguments, and it will produce an observable as an output. And the observable has to match the data. It has to match the type and the dimensions and the units of your data. And you're going to subtract the data from your model function to get residuals. We're going to square those residuals and add them up to get an objective function S. S is going to be a function of the coefficients, because all these residuals are functions of the coefficients, and they're going to minimize over A. The value A hat that gives you the minimum is the least squares answer. So again, I've got all these terms are itemized on the side. If you need to freeze the video and read those, hopefully the 12th graders I think could read this easily. Depending on how far along you are in math, it may be challenging, but if it's challenging, then just pick up some ideas. Okay, so this is the idea. This is least squares in equations. In words, the idea of least squares is that you obtain a data set, then you create a model function that explains your data. The model function has some unknown coefficients. You slide those coefficients around using software or using ad hoc methods. You slide the coefficients around until your model matches your data. The match is defined by the sum of the residuals squared between your model function and your data. And the least squares answer is the value of those unknowns that minimize that sum of residuals squared. Okay. So this completes a linear regression example. We developed our least squares problem statement in the context of linear regression, so we don't need to come up with it. We don't need to use a linear regression to show you as an example of least squares. We've already done that. We're going to move on next to 3 worked examples. I'll start with a ball toss, solving for an asteroid orbit, and solving for an unknown planet. So those are the ones coming up next. Okay, this segment is called a ball toss. The idea is that we're going to kick a basketball across the gymnasium and then solve for its trajectory. We don't have the luxury of chasing after the ball with a tape measure to solve for its track. What we do have is a camera back in the corner, which is going to measure the angle between the horizontal and the line of sight between the camera and that ball. There's a launcher on the floor that kicks the ball off, and it would be nice if the launcher and the camera were coordinated, but they're not. We would like to say that the launch occurs at exactly time 0. That would make the equations convenient, but that's not what we have as an engineering problem. This is a more substantial engineering problem for 2 reasons: because the math model is going to be nonlinear, and because the measurements we have are indirect. We don't have a tape measure to solve for where the ball went. Okay. So this is what the camera measured. You can see the effects of the bounces in here. After about this bounce here, right about here, it bounced off the other wall. Then the ball rolled back underneath the camera, causing this end of the curve to drop down. We're only going to be interested about the first 3.7 seconds of this, because we're trying to solve for the trajectory, and we don't care what happened to the ball after its first bounce. Okay. So this is the data set. It's got camera angle over here in column 3. It's index 1 through 37. Time runs from 1/10 of a second up to 3.7 seconds, just before the first bounce. And the camera angles are these are out here to the nearest 6 digits in degrees. So there's the only error that's being simulated is just the round off after 6 digits. So it's very accurate angle data that we're getting. The first 8 records are identical. That's because the ball was sitting on the launcher for the first 8 frames. And then somewhere between the 8th and the 9th frame, the ball got launched. So plot the data set. Here you can see that the camera angle was down around minus 26 degrees for the first 8 frames prior to launch. Then the ball gets kicked off, and we see the camera profile do something like this. The peak of this is not the ball trajectory. This is the camera profile. The ball was a parabola which peaked somewhere over in this area here. So the challenge is to solve for the ball trajectory, and we know the ball's trajectory is a parabola. So its trajectory will be determined if we have the camera time, the time of the launch, and we have the velocity at the launch, Vx and Vy. You're going to be given some information. You're going to be given the data set that you've seen. Also be given the camera coordinates in the gymnasium and the location of the ball on its launcher. So that's its location prior to launch. And you're going to be given gravity, which is minus 9.8 meters per second squared. The camera coordinates, that shows what the camera coordinates represent. It's the corner of this triangle here with coordinates x camera and y camera. The ball in the launcher has got coordinates x0 and y0. The velocity right at launch is going to be v0, which is a vector with elements vx for horizontal velocity and vy for vertical velocity at launch. So I could have called that vx0 and vy0. I just shortened the terminology just to call it vx and vy. So we're going to use least squares to solve this problem. So if you're going to use least squares, then write it down. I'm calling this it is an equation, but I'm calling it a roadmap. The reason for that is because if your project depends on an equation, every little piece of that equation has a story associated with your project. For example, this time here is that's the time is a time frame produced by the camera. We're going to have the camera frame number times a tenth of a second to give us our time base. This n is going to be 37 because we have 37 points, 37 frames of data before the first bounce, and so on. We're going to need a model function, m, and the model function is going to have to take the form of a function with arguments of time and unknown coefficients. The unknown coefficients are going to be the launch time, the velocity x and velocity y at launch. And that model function is going to have to produce an output that matches the same type dimensions and units as the measurements. So we're looking for a model function that satisfies that form. We need a model function that looks like that. So we're going to have to go devise it, but at least by knowing what it is we're looking for, we have a good clue as to what we have to devise. So as you already know, the trajectory is a parabola. So we can start by writing down the equation of a parabola, y equals ax squared plus bx plus c. That is a good equation for a parabola, but it doesn't help. The reason it doesn't help is because this is an implicit function. This says every point on the parabola satisfies this equation, which is true, but there's nothing about that equation that tells you at what time the ball is going to be at what point on that parabola. So we need a different kind of some other expression for a parabola. We can, if we know the ball coordinates, x and y, we can subtract that from the camera coordinates, xc and yc, to get this horizontal distance and a vertical distance. Then with the inverse tangent, we could calculate this. We could calculate the angle there. So that gets us a good step in the right direction. All we need is the ball coordinates x and y, and we can calculate theta. So now next question is, where do we get x and y? Well, I'm going to turn to your physics classes or your physics lessons for a set of equations for x and y as a function of t. This says that your vertical position or your altitude y is 1/2. It's going to be your initial altitude plus your initial velocity times time plus 1/2 gravity times time squared, 1/2 gt squared. Your velocity, your x component of position is going to be the initial velocity, horizontal velocity times time, plus its initial horizontal position. And then, of course, gravity is minus 9.8 meters per second squared. The reason I'm appealing to your physics class is because otherwise I have no way to explain where the half comes from. Why is this 1/2 gt squared and not gt squared? Well, because physics, it is. So anyway. So we can pull those together to get a model function for the ball toss. That function has got cap t, which is going to be time since launch. It's 0 before launch, so we take current time subtracted from launch time. If it's negative, cap t is 0. Otherwise, cap t is time since launch. Cap t goes into the equation for y. 1/2 gt squared plus vyt plus y0. So if before launch cap t is 0, these terms are 0, and just y equals y0. After launch, we get a transition away from the launch point. Same thing for horizontal position. Horizontal position is going to be its initial position on the launcher plus the horizontal velocity times time since launch. And having y and x, we'll drop those into the equation for the angle theta. Theta is the inverse tangent of the ball coordinates minus the camera coordinates. So that gives us a model function for the ball toss. Then we need some initial estimates for the initial estimates for the launch time, the horizontal and vertical velocity at launch. And I came up with about 12 meters per second for the initial vertical velocity. The reason for that is because this ball is going to be airborne for about 2.5 seconds. And I figured it'd have to be kicked off by about 12 meters per second vertically in order to stay airborne for that long. And the 2 meters per second was just horizontally was just a guess. So with those estimates, we've got a launch time of 1, horizontal velocity of 2, vertical velocity of 12 as our initial estimates. We could take those initial estimates, 1, 2, and 12, plug them into our model function, and that would produce the red line shows what the model function produces as a function of time with those inputs. And the blue dots there are what the camera actually observed. You can see the red line's got sort of the same shape as the blue dots. We could tinker with this if we change that one estimate of launch time of 1 second, change that to 8/10. That would have the effect of moving the entire red curve to the left by 2/10, which would make it a better match. So we could tinker with it until the red line matched the blue dots. But least squares is going to do that. We just need to get an estimate that's sort of close enough that the direct search will converge on an answer. The least squares is going to minimize the sum of residuals squared between the observations of the blue dots and the red line. So and then the direct search is going to modify those numbers until this red line matches the blue dots. So we need to put this into software. We need computer code that will calculate the objective function for the least squares, the sum of the residuals squared, as a function of the unknowns. The unknowns again are the launch time, the vertical and horizontal velocity at launch. So some computer code that does that would look something like this. This isn't actually going to compile it in a compiler, but it's sort of a pseudocode. We'll have a function s, which takes as its argument a vector a. Then it's going to unload that vector into the individual elements, launch time, horizontal and vertical velocity at launch. I'm going to set a sum to 0. Then it's going to loop through the 37 observation records. Going to get time off the record, and then subtract launch time. And if the time in the record is less than launch time, so the t is negative, then the software will reset t to 0. So we get cap t as time since launch. And we'll calculate y, the from 1/2 gt squared plus vyt plus y0. We'll calculate x from vx times time plus x0. That gives us the x and y. Then we go into the inverse tangent for the to get the camera angle. And we're going to subtract the camera angle from the observation for camera angle to get a residual r. And we're going to square the residuals and add them up to get the sum of the residuals. The software is going to return the sum of the residuals squared. So all that big scary equation just drops down to some really simple code that looks like that. We're going to need the software that runs the direct search or the PAL minimization. And in pseudocode, it looks something like this. We'll have a function called ballfit. First, it starts up by loading camera coordinates, loads the initial launch coordinates, and gravity is minus 9.8 meters per second squared. It's going to load the initial estimate for the solution for the unknowns. I had 1 second for launch time, 2 meters per second for the horizontal velocity, and 12 meters per second for the vertical velocity. Those are my initial estimates, so the software loads those up. And software will read the data file. It's got the 37 data points in it. And then it's going to software is going to drive a function called PAL. PAL is the direct search minimization out of numerical recipes. So that function takes as arguments the vector of initial estimates, this AV here, and it takes as an argument the name of that function, S. It takes that function right there as an S, as an argument, so that the PAL minimization knows to call that function, drive in that value for the estimates, and then move the estimates around until S is producing the smallest results that it can find. So when PAL minimization finishes, that vector right there is going to be updated in place, and it will have the least squares estimate as its output. So that's what the software is doing. So next thing is to do is run the software. So here we go. We're going to run the software. Okay, software pops out the answer for A hat. It gave for launch time it gave 0.84 seconds. For horizontal velocity it gave 0.4 meters per second exactly, and for vertical velocity it gave 14 meters per second exactly. So take those 0.84 seconds, or take in here. Let's take the 0.84 seconds, the 4 and 14 meters per second. Make generate a function that the red line is a function of t, and you can see now that the red line matches up with the observations in the blue dots. You can take that, then take your estimates for launch time and horizontal vertical velocity at launch, and calculate the trajectory that we were looking for, that calculates the parabola describing that trajectory. You can calculate some secondary parameters like the highest point that reached was at 10.5 meters. It bounced at exactly 3.724 seconds, and the bounce distance was it landed at a point 13.32 meters on the gymnasium floor. So that gives us the answer, and then we can check to see how well we did. Usually, you don't have a truth value for the things you're solving for. In this case, we do, because I simulated that trajectory, and I put into the equation, I put into the software exactly 0.84 seconds and exactly 4 and 14 meters per second for velocity. So the least squares went solving for that, not knowing that those were exact, but it came up with something that's very close. It came up with 0.8399 seconds for the launch time, 0.399 for the horizontal, and 13.999 for the velocity. And those are very close, very close to the truth. The fit errors are almost zero. And the fit errors would not be that good if the camera recorded angles were not completely accurate. I recorded those out to 6 digits with no simulation of error. If we'd simulated error, you would be seeing some fit error in here. But in this case, it's nearly perfect. So if you didn't use least squares to solve for that trajectory, how else would you go about doing it? Well, you'd probably take the first 3 points after the launch. You'd set up a system of 3 equations and 3 unknowns, and then you'd eliminate variables, getting down to one variable, solve for that, and then plug the answer for that one variable back up into the other 2. So if you do that, you get this equation from the model function. Then you could multiply through by this denominator and then gather terms, arriving down to something like this. Then it looks like it's fairly easy to subtract 2 equations to eliminate y, and not too difficult to subtract the other 2 to eliminate x. So you end up with a 0 on the left side of the equal sign. Then you could multiply through by this denominator to get rid of it because you're multiplying by 0 on the left. Then gather terms and then solve a quadratic equation for launch time t0. So it's the gathering up the terms that's a bit messy. But after you do that, after you've gone to the trouble of doing that, the answer that you get is not very accurate, at least not compared to least squares. I modified the camera data, went back to the camera data and rounded it off to the nearest tenth of the degree for each of the angle measurements, and then ran the least squares again. And then, so the least squares, when I ran it again with camera angles rounded off to a tenth of a degree, the least squares got launch time within a millisecond. It got horizontal and vertical velocity within 3 millimeters per second. The 3-point solution got horizontal and vertical velocity accurate to 30 centimeters per second. So that 30 centimeters error is 100 times larger than the 3 millimeters per second. So what you can conclude from that is that the least squares, in this case, is 100 times more accurate than the 3-point solution. And the reason it's more accurate is because it's using all the data. So this is a key advantage of least squares, is that it can use overdetermined data to gain accuracy in its results. So that completes the ball toss. We've demonstrated indirect data where we used camera angle data rather than chasing after the ball with a tape measure, and we had a system. We had a math model that was nonlinear, and with direct search, the nonlinear was hardly any problem at all. If we were using classical methods, we'd have to linearize the math, linearize the model function, and then iterate on the solution, which is kind of a complication. Okay, our next work example is going to be solving for an asteroid trajectory, solving for an orbit. The title of this section is The Orbit of an Asteroid. Gauss and Laplace were the first to publish the method of least squares at around the year 1800. Gauss made himself famous by solving for the orbit of an asteroid series in 1801. So with that as an inspiration, let's solve for the orbit of an asteroid using high school math and software from Numerical Recipes. So astronomers have detected this. Here's a recording of what that looks like. They think it's an asteroid. And there's some speculation that it crosses Earth orbit. So you've been given the challenge to solve for the asteroid orbit and to determine whether the asteroid will collide with Earth. And the only information you have to work with is a telescope observation data set, Earth's orbit, and Newton's inverse square law of gravitation. So, go to work. To start with, if this is going to be a least squares project, the first thing you want to do is write down the least squares problem statement. It's an equation, but every little piece of it identifies some story with your project. In particular, you're going to need the observation data set, which is going to have time of observation and a telescope angle. And you're going to need a model function m, where this model function takes as arguments the observation time, a list of unknown coefficients, and produces as an observable telescope angle. Your unknown coefficients are going to be the initial position and velocity of the asteroid. So its initial position, velocity, x0, y0, x dot 0, and y dot 0. All right, so your data set looks like this. There may have been some politics getting that data released, but in any case, here it is. There are 12 observations. They are spaced 14 days apart, so once every 2 weeks. And you're given the telescope observation is in the form of an angle. Starts out at 61 degrees and it drops down to -1. So plot that. Your telescope angles, they start high around 60 degrees and then they drop off to below 0. So okay, so you'll need a model function, and it's got to have that form. By knowing the form of the function, you have some clues as to what to look for. The difference between knowing what to look for and not having any idea is the difference between searching for clues and being stumped. So we could, if we have the asteroid coordinates, its xy position, and the Earth coordinates, we can calculate the telescope angle using the inverse tangent, just like we did for the ball toss. That gets us part of the way, it gets us a step in the right direction, because now what we're looking for is something to give us asteroid position, xy position. So the only other thing we have to look at is Newton's inverse square law for gravitation. And that's a differential equation. This has got first order derivatives of position and velocity are given by first derivative of position of x is given by vx. First derivative of y is given by velocity in the y direction. Then the first derivative of velocity in the x direction is given by gravity. And gravity is calculated from Newton's inverse square law, and then multiplied times x divided by r. R is the distance. So the g gives us the magnitude, and x divided by r gives some directionality for Vx and Vy dots. So high school students can read a differential equation, but solving it is more difficult. So since we have a differential equation, we have to solve it. There are two options that I can think of. Option A is to use to solve using Kepler's problem, and we could actually do that. In the Fundamentals of Astrodynamics and Applications, page 101 by David Vallado, there's an algorithm that solves Kepler's equation. We could use that, but let's take a different approach today. I'm going to use something from numerical recipes to solve that differential equation. So, well, back to that equation. The problem with solving this equation here is that position depends on velocity, and velocity depends on gravity, and gravity depends on position. Everything is tied together, and it's all changing at the same time. So how do you break into that and solve for anything? It would be easy to solve if gravity were constant. So instead of having, moving position, changing velocity, moving velocity, changing gravity, let's say we could freeze gravity for a short period of time, then the solution for position and velocity would just be out of a parabola. And we know how to solve that. We did that with the ball toss. In the ball toss case, gravity was minus 9.8 meters per second squared as a constant, so it made it easy to solve. If the acceleration were due to gravity were held constant over short intervals, we'd see a acceleration profile that looks like something like that with little steps in it. At each one of those steps, we could calculate, we could update position and velocity as a little segment of a parabola, recalculate acceleration, do another little step, recalculate, do another little step, and so on. And we would get a solution that's somewhat accurate. It's got the right behavior. So even though this has got a step function in it, you can see that it's following, this acceleration profile is following something that you can recognize as a pattern. That's the acceleration profile for an asteroid rounding the sun. So using that idea, that there's actually somebody actually invented that. His name is Euler. It's called Euler's method. The basic idea is that you take one small step at a time. At each step, you calculate the derivatives. You hold the derivatives constant to update all the things that are dependent on those derivatives for a tiny fraction of a second, like a millisecond. Then, using that new position, you recalculate the derivatives. This shows in pseudocode what that looks like. And again, that's the basic idea of computer simulation. And it's depending if it's somewhat accurate if you make the time step small enough. Fortunately, we've got something much better than that. We can improve on that basic idea. The industry standard for integrating numerical differential equations is Runge-Kutta. I'm currently using some GBS, Gragg-Booleer-Stoer, which is described in numerical recipes. I like GBS because it's accurate and fast. So using GBS, what that gives you effectively is you can start with an initial position and velocity vector, a list of states that are all connected with a differential equation. You can supply Newton's gravity law, the differential equation. You can supply time as the independent variable, run that through GBS or Runge-Kutta, and out pops the position and velocity at some time t. So effectively what that's done for us is it's changed this differential equation here, this x dot equals f of t and x, change that into an ordinary equation as g of t and x0, where x is the initial state and t is time. So since what we want is this profile, we want the position and velocity profile versus time, we've effectively got it here. We couldn't get it with an analytical equation, or if we did, the analytical equation was too difficult. And for some systems, there are no analytical solutions. But anyway, even if we had an analytical solution, what we would be doing with it would be coding it up and running it in a computer. And since this runs in a computer anyway, for our purpose, it's just as good. So the GBS is just as good as having an equation. Okay, so since we can solve for orbits, let's try some orbits and see what happens. These are planets, asteroids, satellites, whatever, orbiting a star, and the star is fixed and not moving, and the objects here that in orbit are not attracted to each other in this example. That's giving us elliptical orbits. We have some fun with it. Put in other orbits, and we can see that those are all going to form elliptical orbits. We can do this is going to form a hyperbolic orbit. And this is going to form a straight line. And all these orbits are closing in on themselves. Like here, this one comes in here. It's going to close back on its original position, and then it's going to trace out an ellipse. So all the orbits they're all conic sections of one form or another. Usually they're ellipses or hyperbolas, one of the two. One of the other things we're given is Earth's orbit. So this is the position and velocity of Earth at time 0, and this is part of the information that's given to you. So we can take this information for Earth's orbit, put that into the simulation, and what happens then is that produces an elliptical orbit. And so to validate that orbit is really an ellipse, I took points around the ellipse and then fit a quadratic. Since the orbit is a conic section, it should satisfy an implicit equation of this type. And then using least squares, I solved for the coefficients at A, B, C, D, E, F, and got these values here. So that sample points around that ellipse satisfied that quadratic to an accuracy of 50 centimeters on a scale of on an Earth's orbit is 300 kilometers, 300 million kilometers from side to side. So he's getting accuracy better than 1 part per trillion, and that's an indication of how good the numerical integration is. We're going to want to, going back to our least squares, we want to implement a software that's going to calculate the sum of residuals squared using it as a function of the asteroid initial position of velocity. And that would, software to do that would look something like this. We have a software function S that takes as an argument a vector. That vector is unloaded to the xy coordinate position and xy velocity of the asteroid. We're going to load the Earth's initial position of velocity from our information that's given to us and set time at 0 for the simulation. And we're going to sum through, we're going to initialize the sum to 0, then step through the 12 satellite observations that we have, or asteroid observations, take time out of the database, and then using GBS and that time and those initial coordinates, update the position and velocity of the asteroid in place and update the Earth's position and velocity. Then having those, we can use the arctangent to get the camera angle, subtract the camera angle from the measured telescope angles, square those residuals and add them up, and then this function S will return the sum of the residuals squared. So in this case, we never had an actual equation for the model function. What we had was a simulation of it, and for our purpose, the simulation was just as good. So we are going to need some initial estimates to when we run the least squares, we'll need an initial guess of where the asteroid might be. So the initial, these are Earth's locations plotted around the sun over the course of the 6 months that we are part of the 6 months that we gathered satellite data. To start off, the telescope angles were all around 60 degrees, which would indicate that the asteroid is someplace up in this area. And as towards the end of the telescope observation, those telescope angles drop down, which would indicate that the asteroid is going to drop in behind the Earth, which would indicate it is crossing Earth's orbit. So based on some guess here, where I came up with an initial guess for where the asteroid might be at time 0. I come up with 3 astronomical units for horizontal position here and 2 for vertical, and a velocity of about -30 and 15 kilometers per second. So if we put those estimates into the model function and plot the angle theta that gives us as a function of time, that gives us this red line using these estimates, 3, 2, -30, and 15, as the initial estimates for the asteroid. And you can see that the red line kind of has the right behavior. It starts off high, should be a little higher, and it rolls off a little too fast. So we could, if we modified these estimates, the red line would move, and we could tinker with these estimates until the red line matched up with the blue dots. But what we're going to do is we can let least squares do that rather than have to tinker with them ourselves. We just need something that's close enough that least squares will converge to the right answer. So this initial estimate is probably good enough. So let's put those into the least squares and run it. Okay, there's the least squares running, and it actually only took 1/10 of a second for the software to run. Software pops out an answer, pops out these estimates for the asteroid position and velocity, and it had the effect of moving that red line until it exactly matched up with the blue dots, which is what the least squares was assigned to do, was to minimize the sum of the residuals squared between these blue dots and the red line. So these estimates give it that match. Okay, so putting the Earth information into the simulation and the asteroid information into the simulation from our least squares estimate, we get this trajectory with the asteroid here. It's rounding the sun here and heading back out. You can see it does cross Earth's orbit twice here, although it didn't collide, at least not in this cycle. We can turn on the angle. This, what the telescopes are measuring is the difference between this horizontal green line and the red line to the asteroid. I'll restart it here. This is the angle. This was the 60 degrees as it started off, and here the angle is dropping down, where it's dropping below the horizon as the asteroid dives in below Earth. So that's what that looked like. So how well did we do? Well, it looks like we nailed it. Since this is a simulation, we have the advantage of knowing what the right answer is for the least squares. So there's something to compare to, and we can find out and get the least squares estimate, compare it to truth, and get an error. You can see there's almost practically no error. And also, since this is simulation, we have the option of simulating the telescope data without any error. So when we put in telescope data that has no error, we get an extremely accurate estimate coming out of least squares. In this case, it was good to a meter in position for the asteroid and velocity of down below a millionth of a meter per second. What that does for us is to validate our methods and our least squares software. We could never get accuracy that good with using actual telescope data, but it's a good idea to if you have the option of doing it with a simulation, to validate your methods and your software, make sure that those are accurate, and then go back and run it again where you add errors to the telescope data. So doing that, I reran simulation using adding 1/2 arc second of random error to the telescope data. That produces that produces a fit error that looks like these. Position accuracy is 4,000 kilometers for the asteroid, and velocity is less than 30 centimeters per second. So that's still a very good solution. That's more indicative of what you could measure with actual data. So taking our asteroid data and plugging it back into the simulation, we can run the simulation again, run it out to over the next 10,000 years, and find the times of closest approach. And the result is that this asteroid should pass within 85 Earth radii about 1,000 years from now, and the closest approach in the next 10,000 years is 49 Earth radii. So if this was a real asteroid, we'd advise that you improve the model by including things like the attraction between the asteroid and the Earth, modifying the asteroid's orbit, and keep tracking the asteroid to make sure that your observation data is really good. If you had this asteroid doesn't look like it's going to impact Earth, but you'd want to be tracking that pretty carefully. So that completes an asteroid trajectory example from our least squares. During our example, we turned a differential equation into an ordinary equation using numerical integration, and we had a numerical integration inside of the optimization, inside of a numerical search. So demonstrating something we can do with today's software. So next step example is to solve for an unknown planet. So that's next. Neptune was discovered mathematically. Uranus was identified as a planet in 1781, and it was tracked by astronomers for the next 64 years. They expected to solve for the orbit just like we did for the asteroid, but there was a problem. There was some kind of anomaly in the orbit. In 1845, two astronomers, Urbain Verrier in Paris and John Adams in Cambridge, England, predicted the location of an eighth planet to explain the anomaly. In 1846, the Berlin Observatory found a planet where it was predicted to be, and it was named Neptune. With that as an inspiration, let's solve for the orbit of Neptune using an anomaly in the orbit of Uranus. First thing we're going to have to do is increase our gravity law to bring it up to a multibody case. Before we had the gravity law where we had a fixed star and we had an orbiter in orbit around the star. If we had multiple orbiters, they did not affect each other. Here, everything in orbit is tugging on all the other things in orbit, and we need a more complicated gravity law that adds up all their interactions to calculate the total gravity on any one of the orbiters. Fortunately, our simulation is almost the same. The Runge-Kutta or GPS is almost the same. Here, instead of having just the position velocity of a single orbiter, we can extend the state vector to include position and velocities of all the orbiters in one great big long list. We can put in the gravity law, which is now this thing, and run through Runge-Kutta, and out pops the a state vector updated to time t, where the state vector's got all the position and velocity of all the orbiters, all having tugged on each other and having influenced each other's orbit. So again, for our purposes, what this has done effectively is it's changed a differential equation that looks like this into an ordinary equation that looks like this. And so, since all we want is the result from that calculation, doesn't matter whether we got it from a simulation or whether we got it from an equation. But in this case, if there's more than two orbiters, there are no equations to describe what their trajectories will be. I'll show you what that looks like. This is the example of a three-body orbit. And you can see why nobody's ever solved that in the general case. There are no equations to describe that motion other than the differential equations. Okay. So this is the positions and velocities of 8 planets and the Sun at midnight on the morning of January 1, 1781. So got this information out of information published on the JPL website. We've got the JPL data has a third dimension, position X, Y, and Z. Here I flattened it down to 2 dimensions for the purpose of our example. The JPL data does not have velocity, but I got that by differentiating the equations for position. And the mass information is available from other sources on the JPL website. So this is going to be our starting location for a simulation of the solar system. This shows the location of the inner planets. Here's the Sun, Mercury, Venus, and the Earth, and Mars, and Jupiter in January 1781. And give that a little bit of motion so you can see those start to move. And the Earth is going to come around here. That's Earth right there. It's going to come around here at 1 year. The year is going to click over to 1782. We can zoom out to include the other planets. I'll make those a little larger. Jupiter, Saturn, and Uranus, and by now 1783, and Neptune's over here. This is the true location of Neptune. And we can speed that up a little bit. Zoom out a little more. And let's hold it right here. This is Uranus. It's going to track down here. It's going to have a point of closest approach down here with Neptune at about 1820, and that will figure in later. We'll need to. We're going to be taking that into account later on. So let's continue. Continue up to 1845. Right there, I passed it. Okay, so by 1845, Uranus had completed about 3/4 of an orbit. Astronomers had tracked that orbit and attempted to predict what it was going to be. That's still moving. And because of the presence of Neptune, there was some sort of problem in their data. There was the orbit of Uranus was anomalous. So what's coming up next? I'm going to run that simulation two different ways. We've initialized the simulation with the JPL data for January 1781, and from that point forward, the simulation will propagate, taking into account all the gravitational interactions of all of the effects of all the planets tugging on each other and affecting each other's orbits. So we initialize once to the JPL data, then propagate forward, where the propagation includes all the interactions among the planets. We're going to run it two different ways. We're going to run it in the first one way, where everything is there except for Neptune. Neptune is missing, and we'll get one set of orbits. Run it a second time where Neptune is present, and we'll get a second set of orbits. There's going to be a slight difference on the orbits of the other planets due to the presence of Neptune in the second run. Then we're going to extract the Uranus orbital information from the two runs and compare them. So running at the first case, we've got the track of Uranus for the case where Neptune is missing. It's initialized to the JPL data and then run forward using the simulation to take into account all the interactions among the planets. This shows the XY track of Uranus that the astronomers would expect to get, because at this point they didn't know about Neptune. If we run that same simulation again, where Neptune is included, we get a slightly different track for Uranus. You can see it's almost the same between those two, but there's a slight effect. Neptune has a slight effect on Uranus and all the other planets, and they're all interacting as a result of Neptune being present there. So this shows the here we've got the telescope angle from Earth to Uranus listed here on they're measured yearly, and there's a disturbance in those telescope angles due to the presence of Neptune. For the case where Neptune is present compared to the case where the astronomers didn't know about Neptune, there's a disturbance in the telescope data, and it's only about 2 arc seconds. But that disturbance is plenty big enough for them to know that wasn't a telescope error. There's something really wrong with their model. There's a similar disturbance in the track, the position track. The blue shows the disturbance in the X component of track, and the red shows the disturbance in the Y component of track. Okay, what I've got here is a simulation that has two planets in it, an orange one and a blue one. And you can see that the orange one has the effect that it's pulling the blue one out of its orbit. The little empty circle is where that blue planet should have gone, but because of the presence of this orange planet, it's being gravitationally drawn out of its orbit. This case is a bit of an exaggeration. These two planets are very close to each other, and this orange planet is massive, but I'm using it as an illustration to show how one planet can disturb the orbit of another. All right, so this is a slide I had up earlier. You can see the disturbance in the telescope angle due to Neptune. This is a disturbance in the telescope angle from Earth to Uranus due to the presence of Neptune. You can see it's got a characteristic shape, like we might have expected from that simulation of the two planets, where one was pulling the other planet out of its orbit. You can see that the characteristic shape where, first of all, that planet is being pulled forward and then it's being pulled back. Astronomers notice that. They notice this characteristic shape that would probably indicate the existence of another planet. And also notice that it's being pulled forward about to the year 1820 and then pulled back. That will be 40 years after the start of the simulation. So that's going to figure in later. So we've got a challenge. The challenge is to solve for the orbit and the mass of Neptune using the anomaly in the orbit of Uranus. We're going to, for this example, you're going to be given all 7 planet data without Neptune. All the positions, velocities, mass, the simulation, everything. You'll have everything given to you with Neptune missing. You'll also be given the actual track of Uranus for the case where Neptune is included. So you're going to use the actual track of Uranus and the simulation of the 7 planets, basically to adjust the simulation of the 7 planets to include the case where there's the 8th planet. And we're expecting that 8th planet to match the original starting data from the JPL data. So to start, of course, if this is least squares, you'd start here. You're going to need a data set. That data set is going to consist of time, and it's going to consist of the x and y coordinates of Uranus taken on a yearly basis, where n is 64 because this is being tracked for 64 years. Before we had this was a single dimension. Our data was a single observation like a telescope angle. Here it's two-dimensional. That there's a slight complication. Usually, you could consider the X track and the Y track to be separate data streams and then process them through sequentially, or you can process them through together. Mathematically, that's going to be the same. You will need a model function. This model function has to take as its arguments time, the time in the observation schedule from 0 to 64 years, and it's going to have to take a vector of unknown coefficients, and this vector of unknown coefficients is a position, velocity, and mass of Neptune. So this we might have an estimate here. This is a variable that the least squares is going to move around, trying to get the output of this model function. The output of the model function is going to be a position a position track of Uranus with a disturbance from a planet, an unknown planet right there. I'm going to compare that to the XY track of Uranus that was actually obtained for the case where there were 8 planets included. Get the residuals, square them, and add them up, and get the sum of the residuals squared. And then least squares is going to minimize that sum of residuals squared by sliding around the estimates for Neptune until the output of the model matches the data for Uranus. Okay. So we'll have in software we'll have a similar function to what we had before. This is almost the same as what you've seen before. There will be a function in software called S, which is going to compute that sum of the residuals squared. Going to pass in a vector A. Software will unload that vector A as a candidate position, XY velocity, and mass of Neptune. Then the software will load up the position, velocity, and mass of Uranus and all the other planets as well, and the Sun. It's time 0 in the simulation will be at year 1781. Then the software is going to cycle through the 64 observations, because we have 64 observations, one every year. We're going to get time out of the observation schedule, go into our simulation, and use that time to update the entire state. The entire state's has got a candidate starting locate. Well, it's got a candidate location for Neptune and velocity for Neptune, and it's got all the other planets in there as well, all tied together gravitationally. So they're all tugging on each other. So that means the presence of Neptune in that system will affect the position track of Uranus. That track of Uranus is going to be pulled out here and compared to the actual track for the case where we had 8 planets. The residuals, the difference is going to be residuals, so it's going to get squared, added up to a sum, and then the software will return the sum of the residuals squared. Okay. So we need initial estimates for the position, velocity, and mass of Neptune. We can't just let the software go roaming far and wide, because it would probably try, or it might try, an orbit for Neptune that causes Neptune to crash into Uranus. And when that happens, the software gets lost, and it either can't converge, or it converges on a wrong number. It has trouble. So we need to start with some fairly good estimates in this case. So we could apply some reasoning and presumptions to where we think that the unknown planet might be. As an initial estimate, we could assume that the orbit of the unknown planet is circular. We know that that orbit is actually elliptical, but what we're talking about here is an initial guess for where it might be, and our initial guess can be circular. We could say that the orbital radius is probably about twice that of Uranus, which would put it out at 40 astronomical units. We could guess that the mass of the unknown planet is the same as Uranus, which would be about 14 times the mass of the Earth. And we know from those earlier slides, one of those earlier slides, this one, that the point of closest approach was 1820, about 40 years into the record. So if the point of closest approach is at 40 years into the record, we can go through some calculations here, do some doodling on paper, a little bit of trig, and come up with a set of initial position velocity estimates and a mass estimate for the unknown planet, for Neptune. We put those estimates into the model function, put those into this GBS right here. So those estimates come in at this point here, and we run the software, get an estimate for where Uranus is going to be, and then difference that from the actual, and we have a known disturbance due to Neptune where the red line is on the x-axis, and we get this yellow is where our initial estimate put us. Our initial estimate would give us this disturbance in Uranus orbit on the x-axis when we know the disturbance was this down this red line. So the yellow line is it looks like it's got about the right behavior. It tilts in the right direction. Also, the blue shows the disturbance, the known disturbance on the x-axis, and the green is the disturbance due to our initial estimate. Both of those they have about the right shape, but they need to be we have to increase their amplitude. So we would get a stronger effect if the unknown planet were closer to Uranus, or if the unknown planet were more massive. So let's do a little bit of both. We can drop the radius from 40 astronomical units down to 32, increases mass from 14 to 20. Run through our numbers here. We get a different set of initial estimates for the unknown planet. Plug those in, and now the yellow line has moved out past the red line. So it's good. We overdid it a little. We overshot. Same on the blue line. This green line overshot the blue line a little bit, but it's getting close enough. We could continue to tinker with these numbers, trying to line them up. But least squares is going to do that for us. As long as least squares is within gets the initial estimate is close enough it can converge, it will go ahead and remove the last of those errors. So with that, I think all we have to do next is run the software. You ready? Here goes. There we go. Running the software. This time it ran for 4 minutes. Okay, so after 4 minutes of computing, it popped out these numbers as our position and velocity and mass for Neptune as of January 1, 1781, which puts it back to the starting time in of our simulation. So those are just numbers. Let's compare. Let's see how well we did. These are shown up here are the initial estimates for position and velocity of Neptune, position, velocity, and mass of Neptune. We estimated our second estimate was 20 mass of the Earth. Least squares fit gave us these numbers here, and in this case we know what the truth is because we generated the data with a simulation and we initialized it with JPL data. So the error in our least squares fit is shown down here. The error is basically, it's very close to zero. We hit it right on. We've got Newton's orbit. We've got its position to within 200 kilometers, its velocity within millimeters per second, and its mass, they're all out to good, better than 6-digit of accuracy. So basically, we hit it right on. The least squares was able to take the orbit disturbance in the orbit of Uranus and use that to calculate the orbit and mass of Neptune. So you've got to ask, where did least squares get the power to solve a problem that difficult? It would seem like you'd have to have very, very detailed knowledge of the interactions of the orbits and the way if Newton's present, if it tugged on Saturn and it moved Saturn, and Saturn tugged on Uranus, which affected Jupiter, all those little interactions, it would seem like you'd have to know what those interactions are and take those into account. But it didn't have to, because what we had was a simulation that our simulation had the benefit of Newton's gravity law, and a simulation includes all those effects. So just by running a simulation, we got all those effects taken into account. And we didn't have to solve some massive equation either. The software solved for the Neptune orbital parameters and mass just by sliding them around until it got a match with the actual data. And it took a lot of computing power to do that because we had a simulation of all 8 planets and the Sun all moving and tugging on each other inside of a numerical search. So that took 4 minutes on a fast PC. It would have taken 4 days on an IBM 370 mainframe computer of just 50 years ago. So that shows you what our current computing power can do for you. I'd like to finish with a slide that I showed before. I skipped over the slide earlier because it was jargon, shop talk. It would, by now though, you know what these terms are. Engineers like least squares because you can postulate a model function and you can fit your model function to the experimental observations. When those match, when your math model and your data match, it looks like you really got something. It can find model coefficients without having to derive them. We didn't have to solve a system of equations. We waited for the software to slide the estimates around until they matched. You can use overdetermined data to gain accuracy. We saw an example where the least square is 100 times more accurate than solving a system of equations. It's more accurate because least squares could use all the data, and solving a system of equations just use a few points in its solution. We could use indirect data. Using the anomaly in the orbit of one planet to solve for the orbit of a different planet is a pretty strong example of using indirect data. So I'd like to include a slide on Planet 9. There's bound to be at least one question on Planet 9, and that would be a great topic for a different speaker. What I've done here is I've used simplified examples from astronomy to illustrate a mathematics tool, least squares. But if we wanted an in-depth discussion of some astronomical topic, then we should get an actual astronomer in here to do that for us. Okay, that's it. Thanks for watching, and have a good day. Bye.